Hello, welcome to a video on section 5.2 part 1 regarding sigma notation and Riemann sums and ultimately the definite integral. So I'm going to start this video at the beginning of section 5.2. I know some of you guys have already seen 5.2, but there were some people who missed last week due to the junior retreat, and of course there are people missing today for junior service day and so forth. So figured a video would be a good thing to do for section 5.2 part 1. And then when we meet again as a class, which will be the day after our test, we'll do section 5.2 part 2, and then we can move on to 5.3 later in the week. So some of you guys, or actually all of you guys, should be familiar with that letter. That letter stands for sigma. It's a Greek alphabet. And what it indicates is that we want to replace and add. So for example, we have k equals 1, which by the way we call the index of summation. That's kind of like a starting point. So we start by plugging in 1 in for k. So that's what the replace part means. Replace k with 1. But right here up top is where we end. So we keep going until we plug in 5 in for k, and we add up all the terms along the way. So you have a1 plus a2 plus a3 plus a4 plus a5, and then we stop. And of course, a of k is our formula. It's what we plug into, or what we're replacing letters with numbers. So hopefully this kind of jogs your memory of how sigma notation or summation notation works. Another thing to keep in mind is that the index of summation makes use of dummy variables. And what's meant by that is that any letter can be used. So notice we did k equals 1, but it doesn't have to be k. It could be x, it could be I, j, l, m, n, o, p, whatever. It doesn't really matter. So like in example 1, we see a sigma notation going on here, and pretty much they both look identical except for the index of summation. Whoop-de-doo. You can still do the same thing. It doesn't matter, j or k. All I know is that I'm going to start with 1, so I have 2 squared. Remember, I'm putting 1 in for j, and the exponent becomes 2, so 2 squared, plus 2 cubed, plus 2 4, plus 2 to the 5th. That's going to be what we get, because you're doing this up to j equals 4. Or in this case, I'm doing up to k equals 4. You still get the same thing. So it doesn't really matter what letter we use for index summation, as long as we're just plugging in the first thing correctly and just keep going in order until we stop. If we do this again, but for a much larger ending point, or we can call this an upper limit, our upper limit's 20, and the formula is j times 2 to the j minus 1 power. If I plug in 1 in for j, I get this. Plug in 2 in for j, I get this. Plug in 3 in for j, I get this. And kind of just keep going until we end, which is 20 for j. So you'd be kind of out of your mind to actually work these out individually. So if you might hopefully remember, the graphing calculator allows us to do this pretty seamlessly. And I don't know why it looks like that. There we go, perfect. So alpha window is where you can locate sigma notation. And usually I'll use x. It doesn't really matter. X equals 1, 20 x times 2 raised to the x minus 1 power. So the calculator can do sigma notation for us pretty quickly. And so apparently it's 19,922,945. So again, alpha windows where you locate sigma notation option 2. So again, in the calculator, alpha window option 2. Okay, so hopefully this review of sigma notation is helping. So now how are we going to apply this to calculus, right? How is this going to play a role? Well, example 3 is kind of the start of that, and example 4 we kind of expand a bit more with the calculus and how sigma notation plays a role. So again, our index summation is k equals 1. So of course I replace k with 1. So that's my first term. F of c1 times delta x1. And hopefully you recognize that delta x is a change in x, right? It's kind of like a width of an interval, kind of like what we did in 5.1. We did LRAM, RRAM, MRAM. And then next term is f of c2 times delta x2 plus dot, 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 dot. And we end off with the nth term. We don't know what n is, so I'm just going to say f of cn times delta xn. So that's, again, how we do sigma notation. And this will be something that will be vital for what we'll do later on in this section and later on this semester, is being able to write sigma notation in that way and being comfortable with subscripts and, you know, realizing that the upper limit is n, so we end with the nth term. So again, this right here is what we consider the nth term of our series. So let's say we have an LRAM sum like this, and of course every single one is being multiplied by, has 0.5 being multiplied, every single term here, which we can factor out like that. So writing sigma notation, let's say we use j equals 1, our index of summation. Clearly we have 4 terms, so I'm going to put 4 up there because we're going from 1 to 4. And the formula is pretty simple, just going to be 0.5 times f of x sub j. So that's our formula because we put 1 in for j, then 2 in for j, and 3 in for j, and 4 in for j. So that's how we write that in sigma notation. So what we just constructed, what we constructed in section 5.1 is something called a Riemann sum. This is a term that we're going to use very often. It's called a Riemann sum. And not because they represent area, but because of the way they're constructed. So let me show what's happening here. So the sum of terms represents width of our rectangle times the height of the rectangle. Sorry for the messy handwriting here. So 0.5 was the width of the rectangle, f of 1 was the height, and then width, height, width, height, width, height. And so we call this a Riemann sum. Now they don't have to be as rigidly constructed as they were for our rectangles of section 5.1, where we had the same width and we had to use like the left corner of the rectangle to determine the height, or maybe the right corner if it was RRAM, or the middle of the top side if it was MRAM. Riemann sums actually could differ in width. That's totally possible. So our delta x's could be different. We don't always have to use the same width. The heights don't have to be left or right y values or interval midpoint y values. It really could be anything. Let me get rid of this. What's going on here? Okay. Hold on a sec. Something weird just happened. Okay. And moreover, the function considered could be below or above the x-axis or both. We always did everything above the x-axis for 5.1. So our y-values could be negative. So the key idea is that the Riemann sum is basically a sum of products. Of width of an x sub-interval, meaning that we're taking some sort of interval and then breaking up the sub-intervals, times, emphasize the word times, we're multiplying, a y value in that interval. So we will see some examples on the next page of how this can look. So let's say we have a closed interval from 2 to 10 for this function here. So we're on page 2 of the notes. And say we want to partition this from 2 to 10, 4 subintervals, but notice the widths are different. They're not all the same. So we're not doing a uniform width here. It could be if we want it to be, but I don't want to. And we create rectangles we did before, both heights equal to any y value. So we kind of have this somewhat open-ended. So I don't know. Let's say I drew something kind of like this here. That's my first interval. Say my second interval has width of 3. I don't know. Let's say I do this here. And the next interval has a width of 1. The next interval has a width of 2, kind of like that. Actually, let me make that a little bit more big. So, a lot of different ways I could draw my rectangles. So, I did it kind of randomly. So obviously my first width was 2, and it seems that my height, I made it 5. Next one I made my width 3, because we're told that. I made my height 4. And again, like, you don't have to do LRM or RRM, it's totally random. You can just pick any y value in that interval. So that's what's meant by a y value in that interval, and of course width of an x subinterval. And then of course my next width is 1, and I made my height of my rectangle 1. And then lastly, oh, actually it should be -1, my bad, because it's pointing down. Next width is 2, and I made the height -½, so it's just 10 plus 12 plus -1 plus -1, so you get 20. So that's a potential Riemann sum. Now, will the sum be the same if we partition differently? Probably not. We'll probably get a different sum because obviously I might, different widths, different heights, a lot of things could change. Will some be the same if we pick different heights interval? Also probably not. So it could vary. But the big idea, which is coming up next, what would happen if for a function like this we add a condition that we now take the limit as the width of the subinterval approaches 0? So in this case, we probably get a more accurate area. And this right here is a big deal. So say the width of the y subinterval was 0, then all subintervals have a width of 0, right? So if your y subinterval is approaching 0, then all of them are approaching 0, right? And so the number of subintervals from 2 to 10 will be infinite. There'll be many rectangles, right? So the key idea is the limit exists. If we could take the limit as the width of the y subinterval is approaching 0. So we're referring to this limit, where basically delta x is approaching 0. Then we get a fixed number for our area of all rectangles. because as I said, we get a more accurate area, and so we eventually would converge on that. And it won't matter how we partition or heights we choose. And this gives rise to a very, very important thing in this class, the definite integral. So the definite integral, which is going to be different than what we've been doing previously, where the first semester was more differential calculus, taking the derivative, rates of change. Now we're going to spend time on something called integral calculus, where we're looking more, not rates of change, but total change. And so the Riemann sum kind of provides a foundation for all that. So just taking a curve, partitioning into rectangles and find the area of those rectangles, but assuming that we have infinite amount of rectangles, because the rectangle is going to be super thin, that is what gives rise to a Riemann sum. And of course, or we use a Riemann sum that gives rise to the definite integral, which again is going to be a very big deal for this semester. Now, how do we create a Riemann sum? So we have to have functions defined everywhere in a closed interval, very important. And we pick a number along the x-axis to divide this into n subintervals. How many? Well, in an example, we created 4 subintervals. How many points do we have to select between A and B? Obviously, we selected 3 points. So let's look back at our example again. So obviously, I had to pick a point here, here, and here. So really, it's going to wind up being n minus 1 points we have to select between A and B. And we label these points like this: x1, x2, x3, dot, 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 until we get to xn minus 1. And since it can't be anywhere, our only condition is that we partition, or sorry, that our condition is like this. So if A is a left endpoint, and then we have a bunch of partitions like this, dot, 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 xn minus 1, and then B. So usually our partitions look like this: x0, x1. This might seem a little confusing right now, but it will make more sense when we do an example. x3, dot, 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 xn minus 1, and xn. Where this we'll call B, this we'll call A, and all this stuff's in between. That's why I was saying we have n minus 1 terms in between A and B. We're making our intervals. So for example, the example that we had top of page 2, so we had 2 and 10 as left and right endpoints respectively, but then in between we have 4, 7, 8. So we have 3 values in between 2 and 10 because we defined our widths to be 2, 3, 1, and 2. Yeah, right here. 2, 3, 1, and 2. So x1, delta x1, delta x2, except for the width of the closed interval with delta xk as the width of the kth subinterval. So delta x1 was 2, delta x2 was 3. So our diagram could look something like this. And actually, the more I think about it, I am going to, no, I think I could finish this off. Actually, how much more of these notes do I have? Yeah, I think it's time to take a little break of this video. So maybe you could, I'm going to do a part 2 or a second installment of this video because I do have to head to my classroom to proctor the F period test. So anyway, let me end this video right now, and there'll be another video picking up from the same place.